Imagine trying to figure out what group someone belongs to in a massive crowd. The simplest, most intuitive guess you could make is to just look at whoever is standing right next to them. This diagram shows the logic behind the one nearest neighbor algorithm. The process is straightforward. The algorithm memorizes an entire dataset, takes a brand new, unclassified data point, and copies the label of the single closest point it can find. We can extend this to K-Nearest Neighbours. Instead of looking at just one point, the algorithm measures the straight-line Euclidean distance until it finds a specific number of neighbors, say 3. Then it takes a majority vote of those labels to decide the new classification. What is striking about this localized rule is that it makes no assumptions about the overall shape of the data, yet by following whoever is closest, it implicitly carves the entire space into rigid decision boundaries. This chart shows those boundaries in what is called a Voronoi tessellation. Every single labeled data point carves out its own distinct geometric cell of influence. If a new point lands inside that cell, it inherits the label of the point at the center. Curious, slightly skeptical tone. This raises a question. Modern machine learning deals with incredibly complex, highly variable data. How could an algorithm this simple, one completely blind to larger patterns, possibly compete? To answer that, we have to look at the absolute limit of statistical prediction. For any given dataset, there exists a theoretical maximum accuracy known as the Bayes optimal classifier. It is a mathematical benchmark of perfection that no algorithm can surpass. In 1967, researchers Cover and Hart published a paper to measure exactly how the rudimentary nearest neighbor rule stacked up against that perfect Bayes optimum. The formula highlighted here shows their central proof. They demonstrated that with an infinite amount of training data, the error rate of the basic one nearest neighbor algorithm is strictly capped. It will never be more than twice the error of the perfect Bayes optimal classifier. This proof establishes a direct link between extreme, localized simplicity and the absolute theoretical limits of statistical performance. But that guarantee relies on the word asymptotic. It assumes you have access to an infinite amount of data, which is physically impossible in the real world. You can see why this matters when we scale up the data. Moving from a 2D plane to a 3D volume spreads data points further apart. This is the curse of dimensionality. Adding features grows the volume exponentially, making the space increasingly empty. This equation shows the samples needed to find a near neighbor grows exponentially with each dimension. In a high-dimensional cube, the vast volume means your nearest neighbor is just as far away as any random point, making proximity useless. Even if you gather enough data, you hit a processing wall. As demonstrated here, calculating distance from one point to millions of others across hundreds of dimensions requires so much processing time that the algorithm becomes too slow to run. Scaling up the dimensions of the environment destroys the algorithm's internal logic. Nearest stops being a proxy for similar and becomes a mathematical artifact of an empty space. Because data points isolate themselves in high dimensions and the calculations take too long, directly applying nearest neighbor is impractical for most modern complex data problems. However, if the dataset has few features, or you use a highly optimized distance metric, the algorithm remains an effective tool and a rigorous baseline for testing more complex models. This summary captures the algorithm's role in the field. It serves as a study in the tension between beautiful mathematical theory and the harsh physical constraints of data. Ultimately, the algorithm demonstrates that the ability to learn from data is dictated by the geometry of the space that data lives in.